Hello all, welcome back to yet another video of today's Lead Code Daily Challenge, and today let us solve today's Lead Code Daily Challenge. The problem is single threaded CPU. Hope this problem should be interesting. So you are given n task labeled from 0 to n minus 1, 0 to n minus 1, and represented by a 2D integer array task where tasks of I is NQ time and the processing time means that the ith task will be available at process at NQ time and it will take processing time to finish processing. So you have a single threaded CPU that can process at most one task at a time and will act in the following way. So it is nothing but this CPU can process only one task at a time. If the CPU is idle and there are no available tasks to process, the CPU remains idle. Hope you understand this point. If the CPU is idle and there are available tasks, then the CPU will choose one with the shortest processing time. So if multiple tasks have the same shortest processing time, it will choose the task with the smallest index. So once a task is started, the CPU will process the entire task without stopping. So the CPU can finish a task, then start a new one instantly. So return the order in which the CPU will process the tasks. So the constraints for this problem is nothing but the n can go up to 10 power 5. So we cannot do a we cannot go for a n square solution. So, okay, these are the constraints for this problem. Task length will be n and n will be ranging from 1 to 10 power 5, and this NQ time and the processing time will be 1 to 10 power 9. So how can we solve this problem? Let us understand this example 1 so that we can get a clear understanding what is the problem. So let us consider these are the tasks. I will name this as 0 task. This is going to be first task. This is going to be the second task, and this is going to be third task. And considering it as 0 based indexing. So at time 1, the available task is the 0th task with processing time 2. With processing time 2. So at time 2 at time 2 the available task is first task with processing time 4, but because this is the NQ time, so that is what I'm meaning by time 2. So at time 2 this first task is available, but this is going to be having a processing time 4, and at time 3 the available tasks are 1 comma 4 and 3 comma 2. Why 1 comma 4 is not included in time 3? Because this at time 1 the single threaded CPU will be started executing this 0th task. So this 0th task takes a processing time of 2. So the time 1 and time 2 will be the CPU will be processing the 0th task, and at time 3 only the 0th task will be released. That is, it will be completing that process, that completing that task. So once it completes the task, it will see for this available task. The available tasks are nothing but this 1 comma 4 and 3 comma 2, and as the problem states, it is going to take the shortest processing time. So we what we can do is, we know that these are the waiting tasks for this current state, time 3. So we can just run a for loop and we can take this minimum processing time, and if there is equal minimum processing shortest processing time, then we can take the minimum index. We can also keep track of index also. It is not an issue at all. So we know that this first task is having a processing time of 4, and this third it is not the third task, it is the second task with the processing time of 2. So what we will tend to take is, I will write the order as well because the problem is asking about the order. So zeroth task is executed first. Now when these are the available tasks, we will choose the shortest processing time, which is the task 2. So we will be executing this task 2, and this task 2, when it is executed, it is going to execute for time 3 and time 4. So till time 4 the CPU will be occupied with task 2. So now what we can do is, these are let us say these are the available tasks for at time 3, and now the CPU will be processing task 2. Task 2 is processed. I will also write here CPU is processing task 0. So this can be kept up. So now what we can do is, at time 4 the available tasks are nothing but 1 comma 4, and other process that is available at time 4 is nothing but the process 4 comma task 3, which is having a processing time 1. So at time 4 these are the available tasks, and at time 5 this is the CPU is going to be processing this task 2, because sorry, at time 3 and time 4 the CPU would have been processed this task 2 and it will be completed. So at time 5 it will be idle, and when it is idle, it is going to take the shortest processing time. The shortest processing time is nothing but the task 3. Task 3 is having a processing time of 1. So the CPU is going to take this task 3, and task 3 is going to be executed, and at time 5 the available tasks are 1 and 4. So at time 5 this task third task will be executed, and at time 6 and at time 6 the CPU will be taking this. CPU takes task 1. So this is the order. We got the order which is expected 0 2 3 1. So hope you understand what the problem states and how it is approached. Actually we go for each and every time 1, time 2, time 3, time 4, and we are what we are doing is, we are actually adding that particular task. What we are actually doing is, we are actually adding that particular task to our waiting list. We can name this as something as waiting list. So waiting list is getting filled, and each time, and for each time when one task is getting completed at certain amount of processing time, the shortest processing time task is taken by the CPU, and CPU gets executing that task. So that is what the problem is doing. So what we can do is, we can run a for loop from time 1 to let us say the longest time that can be is 10 power 9. So we can run a for loop from time 1 till 10 power 9 at worst case, and we can add the certain task into our waiting task, and we can run a for loop. When one task is completed, we can run a for loop, and we can take the shortest processing time task, and we can just execute by that CPU again. But the time complexity for the solution, this is a brute force solution, so the time complexity for the solution will be order of n square. So can we optimize this problem? Can we optimize this searching space in the sense, we are having an order of n in searching time. So if we can reduce that some certain we can reduce the for a certain amount of time, then it can be done in order of n log n. If we reduce that reduce the searching space of order of n. So we are for each and every point of time when a CPU is idle, we are running a for loop of order of n, say in waiting task, and we are getting the shortest processing time. So instead of that, instead of an order of n, we can use a priority queue. Since we need a minimum time, we can maintain a min heap, so that with that min heap will be giving a the min heap will be giving a shortest shortest processing time that we needed, and we can just put we can just insert it into our CPU and we can just process it. So this will be having a time complexity of order of n log n. But even this will be very time consuming if we perform like time we going if we perform like time 1, time 2, time 3, time 4, time 5 and so on. So can we optimize that too? So we can since the NQ time is nothing but is ranging from 1 to 10.9, we cannot go from time 1, time 2, time 3 in a linear fashion, and it is not going to be an order of n at all, because 10.9 is huge number. So this time will be very lot. So what we can do is uh, we can first sort this entire task based on the NQ time, and what we can do is the same approach we are just going to simulate using a priority queue, and we are going to have some variable to keep track of the ending time of the task. What do I mean from this is at time 1. So this is actually this is already sorted in some particular order, right? So we can take this first task. This first task is nothing but first task is starting from start the first task time is starting from 1, and this processing time is 2. So uh, if this task is going to start from time 1, then and it takes a processing time of 2, then this task is going to end at time 3. The ending time, let us say this ending time is nothing but 1 plus 2, which is 3. Obviously we know that the ending task of this ending time of this zeroth task is nothing but 3. So what we can do is we can next run an iteration, and we can just insert the task which are ending from till 3. We can just do an iteration, and we can just insert the tasks which are lesser than this ending time into the waiting task list, which is the priority queue that we are maintaining. So that priority queue is nothing but the min heap that we are maintaining. So we can just insert this first task and this second task. Actually, we may have a case where, consider we don't have these two tasks at all. This is the first task that we are executing, and that ending time is nothing but 3. So at time 3, we are not going to push any task into the priority queue, and if the priority queue is empty, what we can do is we can just push this task. If we are considering these two tasks are not available, then after the zeroth task, this task is the one that we are going to execute as the second task. So we will just directly push this task, so our pointer will be at this position. So if we are having a dry run with this example itself, what we can do is first task time is nothing but 1, and that is going to have a processing time of 2, and it is going to end at time 3. So it is going to end at time 3. Then we are having a pointer, let us say we are having a pointer I at this position. So we will be running on a loop and we will insert all the tasks which are lesser than or equal to that current ending time. This is the ending time, current ending time, which is 3. So this ending time is lesser than 3, and this is the ending time is also lesser than 3. So these two tasks can be inserted into our waiting list, which is the min heap that we are maintaining. So waiting tasks. So these are the waiting tasks that we can say. So we can just push this 2 comma 4 and its id. We can also push this id, which is 1, and we can also take this second task 3 comma 2, and we can also push the id, which is 2. Now these are the waiting tasks. So for the next iteration, my pointer will be at this position. I will be at this position, but for the next iteration we are going to pop out one task which is having the shortest processing time, which is nothing but this 322, and we will just add it to our answer. We are going to execute the second task, and when we pop out this one element, we are popping out this 3 2 2. So we will add this id into our answer we have added, and this is nothing but now my current ending time. Now my current ending time is nothing but the current time is 3 plus the processing time, 3 plus the processing time, which is 2. Super. So the current ending time is nothing but 5. So we will run a for loop again, and we will just push all the tasks which are lesser than or equal to this current ending time, and we will push this into our priority queue, and we will insert into this waiting task. Waiting tasks is nothing but waiting task is nothing but 2 comma 4 comma 1 will be waiting, and 4 comma 1 comma and its task id is 3. So these two are the tasks which are waiting inside this. So and we know that again in the next iteration we are not going we have reached the boundary. I has reached the boundary, but our priority queue is not yet completed. No, priority queue is not yet got empty. So again we will pop out the task which is having a shorter processing time. We will pop out this third task which is having a processing time of 1, and we will add it to our answer, and again in our next iteration we will pop out this and we will add it to our answer. So hope this should work, and we can just implement this in easy fashion with just pointers and having the priority queues. So by this the time complexity will be, what will be the time complexity? The time complexity for this solution will be, we are going to insert at most n tasks, and we are going to have pop out n tasks each and every time. At most we are going to have all the tasks into our priority queue. So the time complexity will be n log n, and the space complexity will be an order of n. So this is our time and space complexity. So let us code this approach, and let us see how it goes. And I think you may learn how to do a custom comparator in priority queue by this problem. Let us have that. Let us do that. So how actually this priority queue is going to have a min heap, and we are just going to insert the process id, the task id, and then the NQ time and the processing time. So so these are the structure that we are going to maintain inside our priority queue. These are the information that is needed for to solve this problem. So we can actually create a struct, let's say process. So let us create a struct name as process, and this process is nothing but it is going to have int NQ time. I will say it as start time. Let us say it as start time, and this is going to be the process time. So and I am also going to have the process ID, process process sorry task ID. Let us say it as task ID. So these are the three information that we need inside this process. One is the start time, when that process is going to be start, which is the when does that process is going to be available, and then the time it take to process, and then the task ID. So we are having a struct. Now what we can do is we are going to have a priority queue. Okay, priority queue, and this is going to be a min heap. So let us first have a simple min heap with integer inside this priority queue, and we can easily change into the process structure. So how to declare a min heap? So priority queue int vector int and then the greater int. So this is how we create a min heap. Let us say this is going to be a min heap. Just change this int to process in into our own data type, which is the process, and this is going to be a custom comparator, so we can say it as or yeah, this is going to be a custom comparator, so we can define this later. This can be defined later. So this is going to be a min heap that is going to keep track of, or that is going to keep track of these tasks. So if the process time is going to be equal, then it is going to sort based on the task ID, and if the process time is but it is going to give the shortest process time. So let us say it has min heap itself. And now what we are going to do is we are going to have a pointer which is at 0, and first itself we can just, it is not assured that it is going to be in sorted order. So what we can do is first we can sort this task vector. So sort of tasks dot begin comma tasks dot end, and we can also use a custom comparator here as well, but it is not needed because if the it is not sorted in correct order, it is going to take the first element only, so it is not at needed, I guess. So yeah, now we have sorted this tasks. What we can do is next we can run a while loop. Mm, what we can do is first, while my I is lesser than n is nothing but the number of tasks, n is equal to tasks dot size. If my I is lesser than n, or if my I is lesser than n, or my priority queue min heap is not empty, if this both condition is true, then we want to process it until all the tasks are correctly inserted into our resultant vector. So we are going to return our order. Let us say it as order. So I will define this vector in order. At the end of the day, we are going to return the order of the task that is executed by that single threaded CPU. So if my I is inside the boundary, or if my min heap is not empty, then what we have to do is we want to go inside this loop. And if my min heap is empty, what we can do? We have two cases, either min heap is empty or either min heap is not empty. If my min heap is not empty, then what we can do is we can have that cases as well. So if my min heap is empty, then definitely this I is going to be inside the boundary, right? So what we can do is we can directly push that particular task into our priority queue. So min heap dot push off that structure. What is that structure? The task, the start time, then the process time, then the task ID. So what we can do is First of all, we want to map those tasks ID as well. We have not yet mapped that tasks ID, right? So we can have a loop for auto ampersand task in my tasks. What we can do is we can just push the push back the ID. So int id equals to 0 id plus plus. So now after that we can just sort it. So by this we can do easily. We can also have a custom comparator. Based on that we can sort that. How we can sort it? Static bool custom comparator vector int ampersand a and vector int ampersand b. And how it is going to be sorted? If my a of 0 is going to be equals to a of 1, what does that mean is it is going to if my if my start time is equal to if my start time is equal, then we have to check for two cases. If my start time is equal, then we can see its processing time. So a of 0 is equal to b of 0. Then if my a of 1 is also equal to b of 1, if the processing time is also equal, then we can just return based on a of 2 lesser than b of 2. So based on id, else just return based on the processing time. A of 1 is lesser than b of 1. If my start time, that is the NQ time, is not equal, then we can just return based on the NQ time. A of 0 is lesser than b of 0. So this is how we can just write the custom comparator for this task. So it is as simple as that. We have the sorted tasks and we are having a priority queue, and we have the ID as well. Now what we can do is we can just push that particular vector. So min heap is empty, so we can just push the ith task. Ith task is nothing but the tasks of I 0, tasks of I 1, tasks of I 2. So we have pushed into our min heap. Once we have pushed into our min heap, we want to increment our I. So this is to be done. Else what we can do is min heap is not empty. If that min heap is not empty, then we can take that one particular task. We can just pop out the first task and we can calculate the current end time of that particular task. So auto cur task. How cur task is nothing but min heap dot top, and we can just pop it out, min heap dot pop. We can later define the custom comparator for this min heap. It is not that complicated, but it is very simple, and if it is easy to understand. So if we can take the cut task, and we have taken the cut task, now we want to insert the cut task ID into our answer. So answer is nothing but order dot pushback of cut task dot task ID. So we have pushed the task ID into our resultant vector. Then what we can do is we can calculate the end time. Int cur end time is nothing but cur task start time dot start time task start time. I don't think so. It is cut task start time. Actually, it is going. It is nothing but the. It is not going to be cut task start time. It is going to be cut end time plus current time, current end time plus the current task process time. Process time. So this is what we are going to add. This current end time is going to be initialized to 0 initially. So hope you understand what I am doing. So we will be adding for this task. So if my current time is initially 0, 0 plus 1 which is 1, sorry, 0 plus 2 which is 2, time is going to be start from 1. So we don't want to have that thank time at 0, it may cause a problem. We can have it as 1. Actually, to get confused, to not get confused, what we can say is we can have the current end time to be starting from this first task start time. Tasks 0 0. So this is going to give the starting time of the current task. So if we take this example 2, then my current end time will be 7 initially. So what we have done is, first time the min heap will be empty, and what we can do is min heap, since min heap is empty, we tend to push the first task to be the 7 comma 2, and 7 when 7 comma 2 is pushed into our min heap, then I will be incremented, and my next iteration current task will be nothing but the 7 comma 2, and we will be pushed into pushing this current task id into our answer resultant vector. Then we will be calculating this current end time. Now my current end time is nothing but current end time is initially 7 plus this process time is 2 and it is 9. Next, in the next iteration, when it takes the current task, 9 plus the processing time, which is nothing but some processing time, which is 4, 13. Then at the next iteration, 13 plus the next processing time. Hope you understand what I'm doing. So we are just keeping track of this ending times. So this ending time will be easier to take the next process and add it to our waiting task. So instead of saying this as min heap, we can say it as waiting tasks itself, so that it will be easier to understand waiting tasks. So this min heap is the waiting task that is going to keep track. So now after we calculating this current end time, now what we have to do is we want to push all the tasks which are having lesser than or equal to this current end time into our waiting task. So while my I is lesser than n, what we can do is we can just check while my I is lesser than n, and if my tasks of I start time, which is nothing but I0, if my I0 is lesser than or equal to my current end time, then what we can do is we can just push into my waiting task of the pushback of the tasks of I. So I think this syntax is only, so we can just copy paste. So waiting task, now my tasks of I task is pushed into my waiting task, after which I should be incremented. That's it. So this while loop will take care of that. Now our sole task is to fill the custom comparator for this priority queue, and I think then our problem is done. So now what we can do is we can fill out this custom comparator for the priority queue. So how the custom comparator for the priority queue is going to be is, you have to keep this in mind. We want to have a struct initially for this custom comparator. If I type it live, then it will be then it will be tough. What I will be doing is I'm going to paste this custom comparator so that it will be easier. So what is the, this is nothing but for, for priority queue, the custom comparator is will be looking like this: struct comp, and we can have any name here, and inside the struct it is going to be bool operator, and this is the syntax you have to keep in mind. And then this process A and process B, your data type and AB, and we want to say how it should be sorted. So if it is going to be a min heap, then it should be opposite of that. This should be greater than. If it is going to be a max heap, then it should be lesser than. So that is the one thing that we have to note it down here. In custom comparator for priority queue, it is going to be in opposite direction. If it opposite, if it is a min heap, we need a min heap, then a lesser than in normal custom comparator in sorting, if we want a minimum element print, we will be doing like this: a lesser than b, return a lesser than b. If we need a max element, we will be saying a greater than b. So what we can do is, in priority queue custom comparator, if it is going to be a min heap, then we want to say a greater than b, so that then only we will be having the minimum element top of it. If it is going to be a max heap, then we should put a lesser than b. So hope you understand what I'm meaning. So how our custom comparator should be sorted? We need the shortest processing time upper. If the if the processing time is equal, then what we will be doing is, then what we'll be doing is, we will be sorting based on the task ID. So first the case will be the processing time. So we can say a dot process. If my a dot process time is equal to b dot process time, then it should be sorted based on the task ID. How I need this task ID? Task ID should be minimum. The smallest task ID should be come first. So we want to say a dot task ID is greater than b dot task ID. Just the opposite. If it is, if we need smaller, we want to have a greater condition. If it we need greater, we need to put a smaller condition. So if that process time is not equal, then we want to sort based on we want a shortest processing time. If it is shortest processing time, then we want to say a dot process time is greater than b dot process time. So this is the custom comparator that we can put, and we can also add this struct inside this solution itself. And this is how our code looks like, and hope the code is fine. I think we don't face any error. Let us try to run and see. One thing I forgot to note it down. What if this, since we have actually having the processing time as 10 power 9, so we are actually adding some 10 power 9 and 10 power 9. If there is more processor which is having a processing time of 10 power 9, then our integer will not fit into our answer, so we can have it as long to be fitted, else we will get a runtime error, integer overflow error. So we can have it as long here. So that thing I need to emphasize here, why I have put this long. So now let us try to run our code. Great, it gets accepted. So let us now submit the code. I think we need to analyze something. Let us see once again. And okay, it gets accepted for these test cases, but one thing I have forgotten what is that is, when we see the waiting task is empty, we are tending to push one task into our waiting task, but our current end time is not changed at all. In when there is when there are some tasks which are waiting, we are changing the current end time and we are pushing those tasks which are having lesser than or equal to this current end time. But when we are pushing one task into our waiting task, my current end time should be nothing but current end time is nothing but the tasks of I0, which is the start time, which is the end due time of that current task. So this line should be added, else it should not work. Logically, if you think, you can get it, what I'm trying to say. So hope you'll understand the solution. I have declared a struct, our own struct variable to handle the process, and then this is the custom comparator for the min heap that we are maintaining for waiting task, and this is the custom comparator for the task with the task ID, and it is going to sort the based on the starting time. And this is where this for loop runs for task, and it pushes the IDs into the task, and I am sorting it, and I am declaring a waiting task, and I have declared some variables that is needed for this, and I have the resultant vector that is we are returning at the end of the day. And I am running a while loop where if my I is inside the boundary or my waiting task is empty, then I have two conditions. Either my waiting task is empty, or there is some task that to be processed. So if my waiting task is empty, I definitely know that I is inside the boundary, so I can push one task into my waiting task. So if I push that one task into my waiting task, my current end time will be set to this starting time of that current task, and my I will be incremented. Else there are, if there are some several waiting tasks, then I want to process the topmost task which is having the shortest process time, and that process time I will take and I will just pop it out, and I will add that current task ID into my resultant vector, and I should calculate the current end time. And after current end time is nothing but the current end time plus the current task process time. And after calculating the current end time, I'm going to run a while loop, and I'm going to push those tasks which are having lesser than or equal to the current end time, which are having the start time lesser than or equal to the current end time, and I will be adding it to my waiting task. Once it is added, this is the menu that we are maintaining. It will be sorted based on the shortest process time, and this should and finally we are returning the order how that process will be getting executed. So let us try to submit our code. Yeah, it gets accepted for the sample test cases. Let us submit the code. Great, it gets accepted on the one go, and superb. Hope you like the solution. You may see it may seem like the video is very big, and I covered my best to save what are all the edge cases that we handle, and how I approach this problem, and how it is how the way I think, and how the problem is intuitive, how we can arrive at the solution. I handled several cases, and I hope you like the solution. And let me know in the comments if there are any suggestions. Let us see in tomorrow's Late Code Daily Challenge. Until then, bye.